Friederike Maechler from Charité University Medicine, and I'll be presenting our poster on behalf of our colleague Darius Rüther, who wasn't able to join us for this conference. Same swab, same clone. This is the question that we're asking. If we sequence Klebsiella pneumonia from a rectal swab, how much genetic diversity is there? Let's start with the background. We're looking at ESBL producing Klebsiella pneumonia, which often colonize the intestinal tracts of hospitalized patients. Colonization doesn't necessarily mean infection, but it may serve as a reservoir for both antibiotic resistance genes and virulence genes. So it is relevant in the context of hospital outbreak investigations. If we do whole genome sequencing, we usually pick a single colony per swab and even per patient. And if the colonies in a single swab differ, if there's substantial genetic variation, we would have to sequence multiple colonies instead. So how did we address this question? We systematically analyzed 10 colony-forming units for the same rectal swab in 10 ICU patients, which were collected in 2019. We Illumina sequenced all of them, which left us with 100 short-read genomes. And we did core genome MLST using the SeqSphere software to group them into clonal clusters and to determine core genome single nucleotide variants, SNVs. And we also did split k-mer analysis, SCAR, to determine pairwise whole genome SNVs, thus also encompassing the accessory genome. SCAR is a very fast and reference-free tool that was specifically designed to determine or to analyze very closely related genomes. What were our results? Most importantly, all the same swab isolates were grouped into the same clonal clusters with a maximum distance of 3 alleles. And regarding the resistance gene content and the virulence gene content, they were almost identical. They carried the same ESBL gene variants and had the same composition and content of virulence genes. Regarding the single nucleotide variants, we differentiated between the core genome SNVs depicted in the heat map on the left-hand side and the whole genome SNVs determined by SCAR depicted in the right-hand side of the graph. Green represents a low number of SNVs. Yellow, orange, up to red represents a higher increasing number of SNVs. And as you can see on the left-hand side, the overall number of SNVs in the core genome was very low, with a maximum number of 7 SNVs in the core genome, as opposed to the whole genome SNVs in the right-hand side of the heat maps, where you can see an overall larger number of SNVs, which might be expected because it's a larger part of the genome. But interestingly, the correlation was between the core genome SNVs and the whole genome SNVs was good, but not perfect. If you look at the swab number 5, you can see 0 numbers of core genome SNVs and up to 22 SNVs in the whole genome SNVs, which may reflect variation in the accessory genome. So to conclude, our findings suggest minimum genetic diversity across same swab isolates, with all same swab isolates assigned to the same genetic cluster, with highly conserved resistance and virulence genes and very few pairwise SNVs. So probably picking only one colony to sequence in the context of transmission analyses is enough, is sufficient. However, the SCAR results, the whole genome SNV variations, suggest that there may be some variation in the accessory genome. So to analyze the mobile genetic elements across same swab isolates, we would have to do long-read sequencing, which we're aiming to do. With this, I would like to end this presentation. Thank you for your attention, and we're happy to take your questions. You can either approach us directly at a conference or reach out to us via email. Thank you.